Yeah, so thanks the organizers for holding this wonderful meeting and letting me present our work, this one. You can hear me. So the theme of this work is basically exception to ergodicity breaking, and that we somehow summarize loosely in this word scarring. So in scar, we use the word scar in a much more general sense. It has been used in very specific senses. But here we use this word scar as a exception to ergodicity that arises due to external drive in closed quantum systems. My collaborators are Ushmi Haldar, Rodrish Moeshner, and Diptiman Sen for these main works. The grad student probably in the audience, Manda is perhaps also in the audience. These are the two references. So let's begin with a summary of the expectations of ergodicity. What happens if the system is ergodic? What kind of expectations do we have naively? So in the level of eigenstates, of course, this is ETH. You have eigenstates of interacting many body systems, which are representative of their microcanonical ensemble. So you take one single eigenstate of a many body system in the thermodynamic limit, do some average of the local observables on this eigenstate, and that is going to be equal to the microcanonical average around a small energy shell around this energy of the systems. This is roughly ETH, and this is equivalent to saying that all local observables are smooth functions of energy. The dynamics, if you do quench, then this intuition translates the fact that you start with a narrow energy wave packet, which has a very narrow energy dispersion, and all other local observables also have a narrow distribution in your initial state, and then you quench it. If this is really a generic system which satisfies ETH in the equilibrium, the non-equilibrium fallout is you get a Gibbs ensemble, because only conserved quantity is the energy, and you apply statistical mechanics modulo this conservation law. Average energy is conserved, the only conserved quantity, and you expect what locally a Gibbs ensemble. Of course, the interstate is in a pure state, so you focus on the subsystem and you talk about local observable. The periodic drive is only conserved quantities. The energy is no more conserved; it's lifted, and what we expect is basically an infinite temperature like local descriptions. So there is nothing to stop you from absorbing energy ad infinitum from your system, and then you go to somewhere in the middle of the spectrum is explored, and you get something which is locally like an infinite temperature state. So, so these ergodicity expectations from the static to dynamics are quite consistent. There are ergodicity exceptions. Like there are many body localized states. If you have strong disorder, then the interactions cannot probably break down the localizations, and you have highly excited states which are very low entanglement, and they are localized, and then there appear some local conserved quantities, random conserved quantities called L bits, and then ETH doesn't hold in this kind of system. And then there are some more mysterious objects, like they're called scars. They occur in perfectly ergodic systems in zero measure. These are highly excited energy eigenstates, but they actually do not satisfy ETH. That's the definition of the scar. Whether this exists in the thermodynamic limit is a debatable question. The dynamics, these also have fallouts, like can have stable MBL systems under periodic drive. You can take an MBL system, if your drive is fast enough and your disorder is strong enough, this MBL state can survive. And the scar states can also be stable under periodic drive. There is in fact a very nice work from our colleagues in ICTS and Arnab Sen will be talking about these stabilities of scars next Monday. So, so these kind of things are also somehow connected with these non-equilibrium expectations, or exceptions are also connected with these non-equilibrium. Our scenario is a bit different. Here we are saying that ergodicity is broken due to the drive in a system which originally doesn't have any non-ergodic signature. completely ergodic system. You're driving it, and the drive generates new constraints that makes it non-ergodic. So it will be in the Floquet setup. So you take Hamiltonian, a many-body Hamiltonian, drive it periodically with time, and basically you observe local operators stroboscopically. And in this setup, you take what matters is the evolution operator over one period, and you can write it always in this form, exponential of some Hermitian operator times t. And this Hermitian operator can be very weird. Actually, it's usually non-local, and no local observable actually commutes with it. So you cannot cannot export the intuitions from local quenched by the local Hamiltonian using this Hamiltonian. Nonetheless, formally you can use it as a Hamiltonian. And then your state after several cycles is basically equal to the state evolved by this time independent Hamiltonian. You want to call it a Hamiltonian, call it effective. So basically then the problem maps to the quench problem modulo the fact that the guy involved is a very non-local guy. And then Marcos already made the work much easier. You know what happens in the quench. You now use the eigenstate of effective Hamiltonian, set of your Hamiltonian, and this is basically the eigenstate of your evolution operator over a period. So this is initial state, some initial state, which is reasonable. You cannot take one or two superposition of one or two of these, but a reasonable wave packet of this. And you have local operators, and you evolve them with time, and then, of course, what you get is diagonal ensemble. Again, Marcos said, and Peter Riemann already has a proof why these things will be very close to the diagonal ensemble, your long-time averages, a very rigorous one. And now we will be talking about this diagonal ensemble because that helps us omitting the time from the problem. So we are talking about basically infinite time limit of everything. So it will be limited by the size. Having said this, let's come to the central finding of our. We take an ergodic Hamiltonian, satisfies ETH. So all its eigenstate satisfies ETH, nothing, no anomaly in it. And we put a strong periodic drive. And what we receive, the emergence of new type of constraints at certain points of the drive parameter space. So, or parameter space, or points or regimes of the drive parameter space. So if you drive it periodically, the expectation is it heats up. It goes to infinite temperature like scenario. And that is indeed true, except in certain regimes or certain points. So we call these certain points or regimes the dynamical scars. And it affects the entire spectrum. Unlike there are special states, special eigenstates of the Floquet Hamiltonian, it actually shows signature over the entire Floquet spectrum. So the ergodicity system fails to thermalize to infinite temperature like states. That's the outcome of this existence of such emergent conserved quantity. And this happens because we show there emerges a local conserved quantity. There is a local conserved quantity which is respected during this drive, then certainly it cannot heat up to infinite temperature. For a concrete example, we take a Hamiltonian of this form. So this has a time-dependent part plus a potential energy part. So this time-dependent part also has a time-independent part plus a drive part. Why we broke this Hamiltonian in this peculiar form, I will come to it later. This notation will be useful. So H0x is a part which commutes with the drive. P is a part which does not commute with the drive. So H0x is this. This has nearest neighbor and next nearest neighbor interactions plus a small longitudinal field. And when you add this transverse field to it, it becomes a horribly non-integrable Hamiltonian. And then you drive the longitudinal field. So we have H0x, which is the DC part of the Hamiltonian, static Hamiltonian, which commutes with the drive. There is a small perturbation, P, which does not commute with any of the things. And we have a drive which is on the longitudinal direction. So this is our setup. So at every moment, this is a non-integrable Hamiltonian because all of the terms are on. Question? So the first thing we see, which is quite interesting, it was actually discovered by the first author of this paper. We quite didn't believe it because we already wrote a paper in this 2015, which says that it should go to infinite temperature ensemble. Yeah, paper is, I think, believed by most of the people in the community, including us before we had this. So the discovery is you ramp up your. So this the question is whether infinitesimal interaction is sufficient to heat up everything. That's the question. The idea is here, if you increase the drive amplitude or scale everything by the drive amplitude, then the interactions become smaller when the drive is larger. Here, the interaction strength are smaller compared to your drive strength. And here, everything thermalizes. You start with a very highly polarized state, which is the ground state of this Hamiltonian. So you have a drive amplitude which is like n or something here. So everything is polarized. So your initial state is here. And if you drive periodically with time, then your diagonal ensemble average of the magnetization, longitudinal magnetization, is 0 up to a threshold value. And then there is a sudden jump. And then beyond this threshold value, initial state is remembered very, very strongly. So we will discuss that this is not just about the initial state. We can take any initial state with some magnetization. It can be otherwise completely random. It still remembers this magnetization. So if you divide the magnetization diagonal ensemble average by initial magnetization, it shows the same structure. It's something like reminiscence of the KAM theorem of classical mechanics. So if you just put some little bit of interactions, perhaps it's not enough to thermalize everything. So the two interesting features of these things is if you look very carefully here in this regime, actually you'll see that larger systems are more frozen. So if you cut across this is the system size dependence, you see the larger systems are more frozen. Another thing, we just plotted 1 minus mx here in the in here, and that shows this threshold point becomes sharper and sharper. These curves become sharper and sharper, and this threshold doesn't move away with system size. That would be an indication that you would need really a very, very large system size dependent field. But it becomes steeper and steeper with growing system size. The sharpest one is this one, equal to 14. And this one is some lower system size, and they tend to cross each other at some point of time. At some point, that assures us that probably this doesn't go away in the thermodynamic way. So now a very curious thing happens if you stay in this frozen regime and start looking at the diagonal ensemble average divided by initial magnetization as a function of frequency, drive frequency. For a very large range of life, actually it goes far, far here. We didn't show it. It can go to 10 to the power minus 3, 4, 5, whatever you want. Frozen. There are particular points where the system remains frozen. So M divided by initial magnetization. So 1 means it remembers the initial magnetization completely. So there are particular peaks here where these things almost absolutely frozen. There are two initial states. One is a pure state. This is the green one. And another is a very high temperature density matrix, which we evolved nonetheless by the Schrodinger evolution. In both cases, this shows a very strong signature. That clearly says that something must be happening over the spectrum, not just initial state is the point. What we did plotted the magnetization of each individual Floquet eigenstates. So this plot. So, and also we plotted the magnetization of the x basis states for comparison. What are the x basis states? These are the simultaneous unentangled eigenstates of all sigma I x's. So these are just those classical states in the x directions enough. These x basis states, of course, have a step-like structure. So there are a number of L choose n kind of scenario, how many spins you can flip. in the magnetization constant. There are degeneracies, and that has a step-like structure. Curiously, for these peak values, where we are saying this something special is happening, corresponding numerically corresponds to this condition, hdx equal to k some integer into omega, the structure of this Floquet magnetization exactly undistinguishably coinciding with this step structure. For example, your drive is 40, so if you take 10, 20, 30, 10, 20, 40, you cannot distinguish it from this black line. If you go a little bit different, like 112.5, for example, or 30, a smooth behavior. So it shows that magnetization emerges as a conserved quantity. So each Floquet state has a one-to-one correspondence with this magnetization at this particular special points, so which we call the scar points. Question is, so one natural feeling would be, so you have a very, very large drive term, so you can neglect basically all other terms. Your effective Hamiltonian is basically has become the drive Hamiltonian, and your Floquet states have become the X basis states. But interestingly, that is not the case. You can take different X basis states, which are of course the eigenstates of your drive Hamiltonian, and measure the entanglement growth at different values of HDX for different frequencies. Interesting thing is, if you take this one, which is all up, you see for small drive amplitudes, of course, everything thermalizes, entanglement grows almost linearly. But with a little bit larger drive amplitude, the entanglement growth for those particular frequencies for which the freezing happens is almost zero. All other frequencies, there is a substantial extensive growth of entanglement. But if you take a different state, it's a double domain wall state, you just, because of the periodic boundary condition, half of them spins are consecutively up and half of them are down. Still an eigenstate of your drive Hamiltonian, but there is a rapid growth of entanglement entropy. So the idea is, though magnetization is conserved, the effective Hamiltonian is not the drive Hamiltonian. The other terms plays enough role to generate extensive entropy. So this is the scenario. So these are different magnetization sectors this represents, and if you drive, really all of them should be connected, and ergodic, everything should go to everywhere. Even that is true for a quench, but if you put a strong periodic drive and put this condition on, then this breaks into the magnetization sectors, and all the dynamics happens within one sector. And these sectors can be very large because zero magnetization sector is almost extensive, and hence you can have a lot of entanglement entropy generated if you, I think this is the back, yeah. If you start with states which are in the zero magnetization sector. This guy is just here, one guy, nobody there in the same magnetization sector, doesn't have place to go because magnetization is imposed as a emergent conservation law, and that's why this guy doesn't have any entanglement group. So the summary is, Mx commutes with H effective, approximate commutation, so it's an emergent conserved quantity, so it's not exact. But H effective is not HT, so Mx is basically HT. So HT commutes with H effective, but HT is not H effective. This can give you a recipe to freeze an arbitrary spin pattern. For example, if you wanted to freeze the half of consecutive half spin up and consecutive half spin down, your drive Hamiltonian has to be chosen like that, so that this state, a bit louder, I can't hear. one? Yeah, yeah. So yeah, so this is an interesting, it's a very interesting question. So yeah, so this is a very interesting question. This just said this mx is not just the only one conserved quantity. There are many others which we are working out. So the structure of the Hilbert space is not as this simple as we are said. There are further structures within the sectors. So yeah, so all the states in one sectors are not uniformly connected with each other. So it depends on which state. So there are further structures which we are still exploring. It's an ongoing project. We will show that. So yeah, so you can pick and choose your drive Hamiltonian and put your target state in the single non-degenerate sector of your drive Hamiltonian, and then that doesn't grow. That fixes the state. So of course there are resonances. It's a many body system. There has to be resonances, and that is supposed to be killing thing that should kill your freezing. And resonances are indeed there. So we vary some parameters in the Hamiltonian. We could vary H0x, we could vary kappa, we could vary J. We just chose this one because it's a nice picture. We studied all of them. This is a nice one. For now, just follow these green lines. So these green lines are the numerical simulation for 14 side, L equal to 14. And this indeed shows that for particular parameter values, there are very, very sharp dips in your magnetization. Basically, magnetization drastically, your freezing drastically get destroyed. You go to longer system size, then you will see these dips become deeper. But interesting, there are no new dips. So this is for very small frequency, omega is 0.04. You could go at smaller frequencies. The results are like this. And then this is for actually a finite temperature result, finite temperature. So these are the dips in the finite temperature results. So we will come to these purple lines, which exactly matches with the dips, which we deduce from some first order perturbation theory. The interesting thing to notice here is the resonances are very sharp. They don't have a very big width. They're not overlapping, and then they are isolated. So there are space between resonances in the parameter space where you can actually have these stable scarce states. The analytical approaches. First, of course, you want to use Magnus expansions because it goes up to very high frequency. And then there is a Floquet perturbation theory which takes care of these resonances, those purple lines, as I promised. Standard Magnus expansion is of this form. You have an effective Hamiltonian which comes through this high frequency series. First term is the average Hamiltonian, but here we have a very large term in your Hamiltonian, the drive amplitude. So these terms are going to be larger and larger as you do the nested commutation. So this is not a good idea to do. In fact, even the first order term, this is the average Hamiltonian, it's qualitatively wrong in our case. Because if you average out the drive, you're left with a non-integrable Hamiltonian. If you start with a magnetized state, it just destroys it. The magnetization goes to zero very rapidly. So the fact that magnetization stays close to 1, if you start with 1, says this Magnus expansion is not going to be very hopeful unless you take, of course, all terms or something like that. What we usually do to get rid of these big terms, we go to a rotating frame where we actually eliminate this large term from your Hamiltonian in the rotating frame. You do this kind of a unitary transformation. This is your drive Hamiltonian, this is your time dependent factor, and then you get in your rotating frame Hamiltonian this kind of a Galilean term. You can adjust exactly to cancel out the large term, and then you get an effective Hamiltonian. And in our case, you just apply this. This is the effective Hamiltonian you get. H0x is this interacting part but all sigma x basis, and you have now a y part and a z part if you do this rotating, you go to the rotating frame. And your large term now goes to this phase. But the Hamiltonian does not have any large coupling. You can do Magnus expansion happily. Magnus is a guy, I guess, after who's, right? I read his papers, so I thought just a name. Yeah. So this is the first term. Looks a little bit ugly. And there are the higher order term, second order term. You can go calculate these several integrals which goes to 0. It's still pretty ugly. The miracle is if you put this condition, all of them goes to 0. And your effective Hamiltonian is just H0x. And interesting thing is it doesn't depend on the form of H0x. It can be any interactions in any dimension. Doesn't matter, any form, any number of terms, any kind of locality. So this result holds miraculously to second order for any kind of H0x. The interesting point is this does not really lift all the mystery, because what we have seen that H0x is not really the Hamiltonian, effective Hamiltonian, just explains the fact that effective Hamiltonian up to this approximation commutes very well with the magnetization. But still the residual terms does something which contributes to exponential growth in entanglement for the states which are in the zero magnetization sector or large magnetization sectors, small magnetization sectors. Yet the conservation of magnetization is very tight. This is respected by all other terms, as we have seen from the numerics. So now we would like to address the resonances. So this is our Hamiltonian. Just rewrite it once more. And then this guy, the time-dependent part, but it commutes with itself for all time. It has a static part, which is all sigma x. It's a drive part, which is also all sigma x, and V is static. So this is the static term, commutes with all time. Since it commutes with it at all time, your eigenstates are fixed. Just have a time-dependent eigenvalue. And the rest is pretty simple. You just say V is a small perturbation because this guy has a very large drive amplitude in here. So 1 by drive amplitude is like the small parameter here. So in absence of V, each of these eigenstates of this guy, time-dependent eigenstates, eigenstates are not time-dependent, they're modulo of phase. These are all naturally the Floquet states. You start with it, it remains there, so it's a natural Floquet states. Our aim is to introduce this V, which is a small number compared to the largest term here, and ask what is the Floquet states in presence of the perturbation. So this is a time-dependent Schrodinger equation. You expand your time-dependent function in terms of this time-independent eigenstate of the time-dependent Hamiltonian, time-dependent part of the Hamiltonian H0t. And then to first order, you calculate these things. It's just like a Dyson series. You just keep the first order. And then this takes this form. So there is a small denominator which gives you the resonances. So if this guy is 0, then your perturbation breaks down and naturally cannot have any, can have something like diverging series, which not necessarily says that there is a thermalization, but if it isn't there, then if there is no divergence, no resonances, probably you can say thermalization is not probably towards the convergence of this. So certainly these are the resonances of this theory. What I'm trying to say is resonance of any theory does not necessarily mean anything physical, but in this case we will see that that's very physical. So in our case, if you put that, then this turns out to be this, because these are the energy difference of H0t. So H0t is a classical Hamiltonian, and it's highly degenerate, but any two of its energy has a single spin flip difference. So basically, to find all the resonance, you have to chart out all the possible energies you can obtain, energy differences you can obtain by just flipping one spin. So now it has next nearest neighbor interactions. So there are 5 spins involved. We have kind of a formula where sigma 0 indicates it's an Ising, classical Ising spin. Sigma minus and plus two other spins on 2 sides. These are all possible combinations of resonances. These are all resonances. And these basically gives the violet lines you have seen in this figure. It accounts for all the numerical dips. So we are almost in the end of the talk. So the idea is, we think these 2 series are asymptotic in nature, because higher order resonances will have a lot of weights, because the number of terms grows with square root of L with system size. So you'd expect that the higher order resonance will dominate the things. However, we see in the numerics, just this formula is sufficient, this first order resonances. Somehow this gives an impression that your series is asymptotic. That is true, then the resonances are isolated, and then indeed this can survive in the thermodynamic limit. So in retrospect, this kind of dynamical scarring dates back quite long. If you take an integrable system, as Marcos was pointing out, this can still have a lot of entropy. And then there are very designated conserved quantities. And if you drive them periodically, then people can show that there are periodically conserved quantities, a set of periodically conserved quantities, extensive number of them, and that describes the periodically driven system in terms of a periodic Gibbs ensemble. It's still quite an ensemble. Cannot guarantee you conservation of magnetization, which is not one of these conserved quantities. There is no reason to believe that magnetization has to be conserved quantity. But in this simple case, actually it emerges as a conserved quantity. In spite of the fact that actual describing ensemble has a set of conserved quantity which is not one of them. Actually, even in integrable system, if you think of thermodynamics in terms of generalized Gibbs ensemble, this kind of dynamical scarring was observed really pretty long back. The conclusion is strong evidence in favor of existence of stable non-thermal Floquet states in interacting systems. 2 types of series expansions and their comparison with numerical results indicate they are asymptotic in nature, and the first order indicates there are only isolated resonances. Possibility of stable non-thermal state in thermodynamic limit. This opens up new possibility that of Floquet engineering in interacting system. Stable Floquet time crystal without dissipation cannot be ruled out. Thank you very much for your attention. This is a conserved quantity in this sense. Each Floquet eigenstate throughout this entire spectrum. So it's plot of the magnetization of the Floquet eigenstates, all of them, from top to bottom, and they match exactly with the magnetization of the X-basis states. That means if you write down a state in terms of these Floquet states, then there can be at most mixing within the sectors, but not between 2 magnetization sectors. And that can gather extensive entropy. So there is a lot of dynamics, yet the magnetization conservation is respected. That's the miracle of this thing. And that is respected quite accurately, very, very accurately.
so I question about this plot exactly.
Yep.
So we see that in order to see the nice quantized step structure, we need high frequencies.
No, 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 no. It can be very, very low. It's actually more pronounced in the low frequency. Just amplitude is high.
The amplitude is high, yeah, but here at least in that plot,
No, no, we showed that, but actually this phenomenology, yeah. So I had a figure which was in another slide from which I was telling things. Actually, these things are much more stable in low frequency. That's most important, because then in terms of naive magnetized expansion, it will look like all higher order terms are important. But in this kind of rotating frame, magnetized expansion is different. And what happens at high frequency is interesting, because if you drive very, very high, then actually you see thermalization here, because you are tending to validate the normal magnetized expansion, very, very high frequency, and you are left with a static Hamiltonian, which is non-integrable in this case. That will decay the magnetization. If you really go to very high frequency, like 100 or something, then this phenomenology breaks down actually. So this is there in this figure. See here, frequency is like 100, something like that. Then it's not frozen anymore. It actually goes to 0.
I have a little bit of problem with large frequency, because when the frequency gets so large at the system size of 40, then it's larger than your.
Right. So
then you don't really.
Right. So you just neglect the drive, right?
Right.
Then you are left with a Hamiltonian. That's what I'm saying. That's exactly what I'm saying. If you go to the beyond many body, it's still a bit it's still half the many body bandwidth. But still, let's say if you go really many body bandwidth, it's like 1,000. You just what you do? Just throw away the drive, because average Hamiltonian is good enough. And our average Hamiltonian doesn't conserve magnetization. It's a non-integrable Hamiltonian.
I mean, at these special points, somewhere you wrote that the commutator is approximately 0, right?
What is
you wrote it's approximately 0?
Yeah.
But you don't think it could be an exact statement, like at some.
Yeah, it depends on the size of your drive, right?
No, so it's not an exact statement. But even commutator actually.
No, I always wrote approximately 0.
So you're sure it's not an exact. It's not.
It cannot be exactly 0, because if you take the commutator, it's not 0. But there are higher order terms, right?
No, I'm saying if you the Floquet Hamiltonian.
Yeah, it's
just
0.
It's not possible that it's actually.
Let me show you one figure where we tried to address this question in terms of dynamics. Sorry. Yeah. So here you see, not exactly 1, but as you increase h, goes to 1 like that. So this is 0.99955, and this is 0.99965. So it's not exactly 1, but it approaches. But that's enough for thermalization. You can have small jiggles around a conserved quantity. That's enough. It has to have a substantial memory of your initial state. That's enough. That it doesn't thermalize. So we call it a quasi-conserved quantity in the sense that there is a fluctuation around it on the average. So it's not exactly conserved, but the fluctuations are very, very small. It becomes smaller for larger system size in this case. I cannot guarantee beyond this system size, because yeah.